Okay, today is chapter 9. It's a brief introduction to what we call statics. There is like a whole textbook and a whole class that's called statics, and you can become very proficient in that matter and become a civil engineer. You can go through, you know, building projects, and statics by itself is a huge chunk of engineering discipline for sure. So today, just a brief introduction, nothing crazy, just some um, balance of forces and balance of torques equations practice, and brief introduction to elasticity on what you have to do when you just don't have enough information from the balance equations. So the importance, clearly, it's the buildings or bridges that should be stable no matter what the wind is, no matter what the climate is, no matter what's going on in the environment. Your project has to be stable and it has to withstand all of those force challenges, and not just forces, but also torques. So statics provides an idea of equilibrium. Equilibrium is just a fancy word for balance. Every time someone says equilibrium, just think balance. So here's an example of a balance of equilibrium. It's the book resting on a table, or a rotating fan with no speeding up, slowing down, or a bicycle wheel that rolls with constant speed. If you'll take a closer look at any of those objects, you'll see that linear acceleration of the center of mass has a value of 0. And what's also important, not only linear acceleration, but also angular acceleration. The alpha parameter that we discussed for rotation for the center of mass is also 0. So you do have certain kind of motion. However, accelerations are 0. And you remember how the second Newton's law connects acceleration to the net external force or net external torque. So for net external force being equal to 0 and net external torque being equal to 0, which is the consequence of accelerations being equal to 0, you say that the object is in balance. The objects are in equilibrium. So two options for equilibrium. It can be either static equilibrium or the equilibrium that is not static. You do have motions. Okay. So first one is the static. So no motion whatsoever. Book is at rest on the table. At rest means normal force counterbalances the gravity. So N is up, gravity is down. You have positive value for this vector, negative value for gravity, and overall net external force is equal to 0. So static equilibrium definitely satisfies the sum of all forces equals to 0. Balance of forces, that's what you call it, because if it's equilibrium, that means balance, and equilibrium, like static equilibrium, is for sure balance as well. So net external force acting on an object is equal to 0, and the object is at rest. The object is not moving. An example can be also the balance of this lights setup, the ceiling. The light setup is connected to a ceiling with 2, 3 different strings, ropes, or cords. And the question is, what kind of tension do we have in chord A and chord B? If there is a load of, 1960 newtons, so this is the weight of the load. So balance of forces, you say net external force is 0, and you clearly have two dimensions here, x and y coordinate system. For x-axis, you have positive f sub b. If this is 60, then this is 60, so f sub a has a negative, and it's a cosine function because the component is adjacent to that 60 degrees angle. So positive fb, negative f sub a times the cosine, because we're talking adjacent component, equals to 0. So no acceleration. That means the right side for the second Newton's law becomes 0. On to y-axis, see how f sub b is perpendicular onto y-axis, so nothing for f sub b. F sub a has a positive component, and if this is 60, this is 60. So this side is opposite to 60, so the function is a sine, and it's positive because f sub a has a positive direction for its y component. Take away the gravity, take away the weight of a load that is given, and everything is in balance, so equals to 0. So balance of forces right there speak for itself. You can solve for either of the tension forces or the load. If the load is not given, let's say, what is the maximum load that you can put on this system? So if it's not 1960, but rather something unknown, then you can still solve it and figure out how much of a load you can put on this system. Let's take at this little setup. You see how there's a ruler that rests on the table. And let's say there is a force that acts to the left, and then the force on the other side of the ruler that is acting on the right side. So what do we see? We see that the net force acting on a ruler is 0, right? Because you have 5 newtons to the left, 5 newtons to the right. You add them up, and for vector addition, you'll just get 0 vector force. But if you put a ruler on the table and start pushing it in this way, you will see that the ruler will rotate. So will that be equilibrium? Well, turns out no, because there will be some angular acceleration. It will be rotating, so you'll get some torques involved in this setup. So it turns out that just the balance of forces is not enough. It is a good condition. It takes care of, say, the book sitting on the table, but it's not enough to ensure that the system will be in equilibrium. You have to introduce the second condition, which is right there, and the second condition takes care of all the possible rotation motion. So in order to make sure that there's no rotation, you set the torques. The net external torque equals to 0. So there can be some stable rotation, but linear acceleration must be 0, and therefore the net external torque is 0. Once again, two conditions. Linear acceleration is 0, and angular acceleration is 0. If linear acceleration is 0, then net external force is 0. If angular acceleration is 0, then the net external torque turns out to be 0. Those are the conditions for equilibrium. Stable or unstable, doesn't matter if it's equilibrium, it's in balance, you have to follow those two conditions. It's only static when there is no motion whatsoever, but if there's still motion, it can still be equilibrium. So be careful with definitions. So two conditions are met. That means the object is in equilibrium, it's in balance, and all the problems that we're going to solve will follow those two conditions. Net external torque is 0, and net external force is 0. Oh yeah, here we go. So this is the slide that summarizes it all. Sum of all the forces is 0, and sum of all external torques adds up to 0, no matter what the axis of rotation it is. Yeah, any possible axis of rotation should give 0 for the net external torque. Otherwise, it's not equilibrium. Otherwise, you expect some kind of acceleration, and your object is definitely not stable. There's going to be problems if, let's say, your bridge gains acceleration, the bridge starts moving back and forth, up and down, and starts rotating. That's not the condition you want your bridge to go through, right? Or a building. If there is strong wind and your building follows the direction of that wind, the building might collapse at some point, and you don't want that. So let's practice. Let's solve some problems. Here is a table, and there is a huge, I don't know, printing press that is sitting on the table. And your job is to figure out the load on the legs of the table, F sub A, F sub B, so two sides of the table. What kind of a normal reaction force you have from the table, so that the table doesn't collapse, so that the table withstands this load. So first condition, balance of forces, net external force equals to 0. What are the forces? Well, there is reaction from the left side of the table, reaction from the right side of the table, gravity of like the weight of the printing press, and the center of gravity for the table itself. So table is also, there's some kind of a mass for the table that you have to take care of, the load from the printing press, and two normal forces from the table that we are looking for. So for forces, they should be in balance. You have some forces that have the same direction onto y-axis, the positive. So F sub A is positive, F sub B is positive, but gravity is in the opposite direction. So gravity should have a negative component. So positive F sub A, negative gravity for the table, and also negative load from the printing press, and positive reaction force from the right side of the table equals to 0. Remember, acceleration must be equal to 0. This is your balance of forces equation. And then the second condition, balance of torques. So net external torque is 0 because angular acceleration must be 0 for the equilibrium conditions. And this should be valid for any point. Like, you are free to choose any point on the system, and no matter what the point is, torques should add up to 0. And in here, you really want to make a clever choice on that axis of rotation, so this helps you to solve a particular problem. The recommendation is as follows. You should always look for an axis of rotation that will eliminate one of the unknown forces, namely, like, let's say point B. Let's pick point B, and F sub A is unknown. What do we know about the torque from F sub A? Well, torque is moment arm times the force by itself. And what is moment arm? Moment arm is the shortest distance between the line of action and the axis of rotation. So if the axis of rotation that you choose to be right here, point P, then the line of action for f sub a crosses the axis of rotation, and the minimum distance between the axis of rotation and the line of action is 0. So moment arm is 0, and therefore the torque from f sub a with respect to point P being the axis of rotation is 0. So you don't know what the force is, you have to find the force, but you can say that the torque from f sub a with respect to this axis of rotation is 0. It doesn't matter how strong the force is if moment arm is 0, because the shortest distance between the line of action and axis of rotation is 0, then you don't care about that force. The torque is 0, moving on to the next given condition. So point P is a very good choice to eliminate the torque caused by force F sub A. Another good choice would be the other side of the table. It's not, there's no particular point for it. Let's say point, I don't know, point B, because it's F sub B. If you choose this point to be your axis of rotation for the balance of torques equation, then the line of action from F sub B would cross the axis of rotation, and therefore the minimum distance between the line of action and axis of rotation is 0, moment arm is 0, so the torque, which is force times the moment arm, becomes 0. So this point, or point P, those are the best candidates for your solution and eliminating one of the unknown forces. You don't know the force, but you know for sure that torque is going to be 0 because of the minimum distance between the line of action and axis of rotation being 0. So for point P, I say F sub A produces 0 torque because line of action for force F sub A crosses the axis of rotation. Next force is gravity from the table, and the line of action, that's what I'm showing right now, up and down, and the minimum distance between this line and the axis of rotation is this distance. It's the perpendicular, so the line connecting point P and the point of application of the force. This line is 10 meters long, so it's 10 times the 1500 G. And don't forget the torques can be positive or negative. So this particular force would create clockwise rotation. And if it's clockwise, remember clocks are negative, so you would get negative torque, and that's exactly what you see here. So negative, moment arm is 10, because this is the shortest distance between the line of action and axis of rotation. And the force by itself is 1500 G. This is your gravity from the table. Next force is gravity from the printing press, from this load. Once again, this is the line of action. Up and down, you extend this line, and this is your line of action for this force. And this is the axis of rotation. So the minimum distance is 10 and 5. So the total is 15. So moment arm is 15. Force is 1500 G. And once again, this force would create rotation in the counterclockwise direction. That means the torque is going to be negative. So this is another negative. 15 is the moment arm because it's 10 and 5 meters. And 15,000 G is the force of gravity from this printing press. So moment arm times the force. Last force is the reaction from the right side of the table, F sub B. That's the line of action. This is the axis of rotation, so the shortest distance between the line of action and the axis of rotation is 10 and the 5 and another 5, so the whole thing is 20. 10 plus 5 plus 5, so it's 20. That's the moment arm, 20 meters. Force is unknown. It's F sub B. We don't know how many newtons there are. But this time, the torque is positive. See how this force creates a counterclockwise rotation with respect to the axis of rotation being point P. And that means the torque is positive. 20 is the moment arm, 10 plus 5 plus 5, and the force is the unknown force that we are looking for. That's it. Physics is over. You have a system of two equations, two unknown forces. From the second one, you can solve for F sub B, plug it in into the first equation, the balance of forces equation, and solve for the unknown F sub A force. So both forces can be figured out. You can solve for both forces. This is your general approach for any kind of problem in statics. You say balance of forces and use some kind of a component that makes the most sense, maybe both components. And then balance of torques, once again, with respect to any point that can be the axis of rotation. And you have to be very clever with the choice of that point. Make sure you choose a point that will help you to eliminate one of the unknown forces, making the torque equal 0. That's exactly what happened to force F sub A. If this is the axis of rotation, line of action crosses the axis of rotation, minimum distance is 0, moment arm is 0, torque from F sub A is just 0. Note, if force comes out to be less, then it's yeah. See, we don't know. If you don't know a specific direction for the force, for the unknown force, and we will actually hit some kind of a problem that dealing with hinges. In hinges, you can get any result possible. So if you don't know and you make just a wild guess on that unknown force, watch out for the values. If a value for F sub B or F sub A comes out to be less than 0, if it's a negative value, that means you guessed the direction incorrect. And physics actually tells you, hey, you got a negative result. That means your vector is pointing in the opposite direction. I remember we did that with conservation of momentum problems. You had to choose a direction of motion after the collision. And if it was not given to you specifically, you had to make a wild guess on which way will the ball go and watch for the velocity. Is it positive or negative? And if it's negative, then you guessed it incorrect and you say, hey, momentum and velocity is in the opposite direction. Same thing happens here. If force comes out to be negative, you don't have to solve the problem from scratch. Again, you just say, oh, the magnitude is the same, but direction for that particular force is in the opposite direction to what I chose to be the positive. So you have two major things to remember. If there is a cable or a cord or a string, then tension is always along the cable, the cord, or a string. There's no way for a tension to be pointing in any other direction. It's always along the cord, along the string, along the cable. But if there is, excuse me, the headset turned off. But if there is a rigid device, namely hinge, then any direction is possible for the reaction force from the hinge. So hinge, anything is possible. Cable, cord, or string, it's always along the cable, along the cord, or along the string. The tension is always like that. Yeah, and you have to eliminate unknown forces by picking the correct axis of rotation so that you eliminate one of those forces by setting those torques equal to 0. So this is your general strategy, and we'll definitely practice it here. So here is a little problem that the textbook has, the diagram, and it shows you both things. There is a cord that supports a certain load, and the same load is connected to the hinge via a rigid structure. So both cord and the hinge are present. And once again, if there is a cord, then tension is always along the cord, and there's no way for the tension to be pointing in any other direction. It's always along the cord, along the string, along the cable. But for a hinge, as you can see, you have some y component, the vertical component, you have some unknown x component, and then there is a vector sum between the two components, and this f sub h, f sub hinge, is just a random direction which you can't predict, you can't guess, you just have to solve for it based on the other components that you have from other forces. Remember, you do x components separately from y components, and then you get net x component, net y component, and after that you can do the net result for the vector. You'll get the magnitude from the Pythagorean theorem or the distance formula, and then you do the reference angle based on the direction of those net components. So what would be the best choice for axis of rotation here? Of course, you want to consider the hinge being the axis of rotation, because no matter which direction the reaction force points at, the torque from this force will always be 0, because the minimum distance between the force, the line of action, and the axis of rotation is 0, and torque from this hinge reaction automatically becomes 0, and that will help you to solve this problem. Do not pick the center of the rod or the point where the cord is connected as your reference axis of rotation, because it will not eliminate the unknown hinge reaction force. So hinge is always your axis of rotation. This way you will solve the problem right away with no problem. So let's take a look at what we have in terms of balance of forces first. So balance of forces, two components, x and y components. Let's take a look at the x components. What do we have? You have the hinge in the x axis. It's positive. You can see that this component of the hinge is positive, and gravity is perpendicular onto x, so nothing from gravity. Nothing from gravity from the load as well. This bookstore sign is the load. Of course, it pulls on the system, but this gravity is perpendicular onto x. Every time a vector is perpendicular, its component on that axis is 0. And the tension force, see how the x component of the tension force is pointing in the opposite direction, and that's why it's a negative component. And everything is in balance, everything is in equilibrium, so the right side is just 0. Your acceleration part is always 0 for equilibrium problems. Onto y-axis, what do we have? We have positive hinge reaction. We have negative gravity from the rigid rod. We have negative gravity from the load. And we have positive tension component, y component, because it has the same direction as the y-axis being positive upward. So plus, minus, minus, plus equals to 0. 0 is your condition for equilibrium. So nothing tricky here. just regular approach with solving vector equations by components. And the trick part is the second condition for equilibrium, the balance of torques equation. See, it says always look for the best axis of rotation. What is the best axis? It's the one that eliminates an unknown force right away. And of course, the hinge is your worst enemy here. So picking hinge as an axis of rotation creates the condition where the line of action from that hinge crosses the axis of rotation that you choose for your balance of torques equation and makes the torque from this force equal to 0. Zero moment arm means torque from this force has a 0 value. It doesn't matter if you know this force or not, the torque from this force is already 0. Ta-da! It's not eliminated, but just the value becomes 0. That's a very useful trick to eliminate one of the unknown forces. So if hinge is the axis of rotation, then the torque from F sub h is just 0 because the line of action crosses the axis of rotation. Minimum distance is 0, moment arm is 0, torque is 0. This gravity with respect to the hinge, this is the line of action. That's the axis of rotation. So the moment arm is the shortest distance. Shortest distance would be half of the total. If the total is 2.2 and the gravity of the rod is right in the middle, then it's 1.1 meter. So 1.1 is the moment arm. Force is mg. Is it positive or negative? What kind of a rotation would that force produce? That force would have produced clockwise rotation. So the torque is negative. Negative torque. Force is mg. And moment arm is the shortest distance between the hinge and the axis at the line of action. So 1.1. That's the first expression. Second force is the load, the gravity from the load, the bookstore sign, pulling it down. And this is the line of action for the force. And that's the axis of rotation. The shortest distance between the hinge and the line of action becomes 2.2. So 2.2 meters. That's the moment arm times the mg, the capital Mg. Is it positive or negative? The rotation from mg is clockwise, so that means the torque is negative. Clocks are negative. So negative, force is mg, moment arm is 2.2, so this is your torque from the capital Mg force. One last force is tension. Tension is always along the cord. Remember, there's no exception for this rule. If there is a cord or a rope or a string, the tension is always along that cord. And if theta is given, right away you're going to know the other two components. So this would be Ft cosine theta, that would be Ft sine theta. So as usual, we did that before. However, it's only the tangential component that we're really looking at, because your x component, see how the line of action would cross the hinge and you would not get any rotation from this component of tension. Only the y component is the component that creates rotation. So F sub Tx gives you 0 torque because the line of action crosses the hinge and minimum distance is 0, moment arm is 0, and Ft sub x would never rotate anything. In this system, it's Ft sub y, which will start a rotation. So if there is Ft sub y, that's the force, that's the line of action. The axis of rotation is the hinge. That's the smallest distance between the line of action and axis of rotation. This is 2.2 meters. Positive and negative, well, Ft sub y creates rotation counterclockwise, and counterclockwise means it's got to be a positive. Torque, so force, moment arm, and everything is positive. This is your expression for the torque from the tension force. Yeah, don't forget to say equals to 0 because it is the condition for equilibrium. The right side is always 0. So what do we have? We have 1, 2, 3 equations, and we have small mass, capital mass, and something else as unknown. So you can solve a system of 3 by 3. And once again, it doesn't matter what's given. It doesn't matter what you want to solve for. You have 2 equations from balance of forces. You have at least 1 equation from balance of torques. This should be enough to solve your statics problem and determining either the load, the maximum load that you can put on the system, or how much of a hinge reaction you would expect and in what direction, or you solve for tension, force, doesn't matter. Physics stops here. If you can create those 3 equations, then my mission is complete. That's what I will be grading in your work. So make sure you understand the components that make up those 3 equations. 1, 2, 3 equations. This is your bread and butter if you are an engineer trying to figure out the load on a certain system. Yeah, not only engineers, but also biology, doctors, nurses, see how you have muscles, and muscles pretty much produce those forces, and joints give you reactions. You have certain forces from different parts of your arm or leg or any other, set of joints in muscles. So you'll be solving the same kind of problems if you are into healing program, like, or you want to set up a certain stress on the joint so that it can be, moved to an original condition. All sorts of muscles and joint problems deal with statics. Yeah, you can see the person bending in a certain way, and there is a certain stress on muscles. So all of those forces that you see, they enter the conditions for equilibrium, and that will allow you to solve for any unknown force, unknown stress. That's the application for biology majors and medical programs. Same equations, balance of forces, balance of torques, end of story. Yeah, you will have either a stable equilibrium when a little bit of a disturbance leads back to the original conditions, or it's unstable. So unstable, think about a pencil that you can balance vertically, and then you introduce a little bit of a disturbance, pencil falls, and it will never go back to its original state. So that is unstable equilibrium. Either way, if it's equilibrium, you still have balance of forces and balance of torques. Okay, here's another problem. You got a rod in static equilibrium. Once again, static means no motion whatsoever. It's just sitting still. If it's non-static, then it means it's moving in a certain direction, but constant velocity. No change in direction, no change in magnitude. And we want to know the second force by balancing torques. Where do you place a rotation axis? Magnitude of F2 is given. What's the magnitude of F1? Okay, so here's the problem. You got 1, 2, 3, 4, 5 forces, and only 3 of those forces are given. You have 20, you have 10, and you have 30. So F sub 1 and F sub 2 are unknown forces. And the question is, how can you solve this problem with 2 unknowns and only 1 equation from balance of torques? Well, you can only solve it when you put your axis of rotation either where the force F sub 1 is applied or where the force F sub 2 is applied. And if you put it right here, where F sub 1 is applied, then the line of action from F sub 1 would cross the axis of rotation. So moment arm is 0. The shortest distance between the line of action and axis of rotation is 0. Moment arm is 0. Torque from F sub 1 would be 0. And with that 0 torque, you say there is a torque from 20, there is a torque from 10, plus 0 torque here, plus torque from 30, and minus or plus F sub 2 times whatever the distance. So there is a torque for F sub 2. You can solve for F sub 2 right away. So you eliminate one of the unknown forces by choosing the axis of rotation right here, or maybe right there if you want to eliminate F sub 2, because this is the line of action for F sub 2. If you choose this as your axis of rotation for your balance of torques equations, then torque from F sub 2 will be just 0. So either this point or that point, that's the wise choice for balance of torques equation. Once again, it's your choice. You can choose any point as axis of rotation, and it should follow that condition if you want the equilibrium. So place the rotation axis at the location where F1 is applied to the beam. This will make it a 0 torque from F sub 1. What's the magnitude of F sub 1? Okay, let's solve it. You got F sub 2 as 65. So you got 20 positive, 10 negative. F sub 1 is unknown, 30 negative, and F sub 2, 65. So 65 up. Balance of forces plus 20 minus 10. What's that? That's positive 10. So 10 minus F sub 1 minus 30 plus 65. When you will do the math, you should end up with 45 newtons. Well, let's do all the top forces. 20 plus 65. You have total 85 up. So 85 up. You got 10, 30, and something unknown down. 10 plus 30 is 40. And you need the balance of forces. You need all the forces to add up to 0. So F sub 1, yeah, it should be 45 because 45 plus 10 plus 30, that will be the counterbalance for 65 and 20 upward. So balance of forces for 45 newtons and balance of torques to eliminate F sub 1 and solve for F sub 2. Or eliminate F sub 2 and solve for F sub 1. This is the axis of rotation, or that is the axis of rotation. That's a wise choice for that. If you choose any other point, let's say you want to choose this point, you will end up with 2 unknown torques from 2 unknown forces. And with 2 unknowns for one equation, you can't solve it. So do not choose this point, do not choose that point, because you're going to eliminate one of the known things. You have to eliminate what is unknown. Okay, on to elasticity. Honestly, there is like huge tables, textbooks on its own, and a lot of information on different materials for different stresses and strains. In this course, it's only going to be just the basic introduction. I will only require you the linear elasticity, And why do we need that? Because sometimes 3 equations that you get from balance of forces and torques is not enough. You just don't have enough things being given. Let's say for that problem where we had the bookstore sign, let's say you don't know both forces, and let's say you don't know all the gravities. What are you going to do? But you still have to solve it. If there is not enough information given, then you would still create those equations, the balance of forces, balance of torques. And if you have 3 equations, let's say you have 4 unknowns, then you only need 1 more equation to close the system. And that last equation can be obtained from elasticity. The elasticity parameters, if you know specific materials that are included in the system, you can try to get the 4th equation that will close your system, and you can solve it after that. So 3 equations, 3 unknowns, solve as usual. You don't need any elasticity. But if you have more unknown things, that's what we call indeterminate case. You can't determine the outcome. Then you go to elasticity, which is a separate branch in physics, and you undergo you will see through those tables how much of a deformation you expect from that system if a certain materials are used. So you can solve those indeterminate cases with extra equation that comes from elasticity. That's the big idea. And elasticity is based on Hooke's law. Remember, for any spring, we had that spring constant, the stiffness. Well, if you'll take a closer look at any material and you put it under some stress, under some force that is trying to compress it or extend it, you will see that there is a little bit of elongation. And that elongation, with respect to the force that you use to create that elongation, can give you this parameter, the stiffness. And from this Hooke's law, you can figure out either the unknown force or the stiffness or anything else that will allow you to solve the statics problem. So Hooke's law, it's like your spring force, but it's not like a spring. It's just a solid object, the extended object of a certain geometry that you can use to figure out the stiffness of that object. And for any object, there is what we call an elastic region, and you should always remain within that region. And after you reach a certain stress that you put on that object, you go into plastic region and eventually the breaking point. You should never ever do that to your real system because you're going to destroy the system if you put a more stress than the system can withstand. So beyond the elastic limit, the material is permanently deformed, and we don't want that by any means, because you want that whole system to be stable. There's one more application that I want to tell you about. Have you ever wondered how we determine the stiffness of bridges? Like, how do we know that a certain bridge is due for a reconstruction? How do we know that that bridge needs repairs? Well, we put a certain stress on the side of that bridge, and we see how the material that the bridge is made of reacts to a certain stress. There's like a special device that creates a little bit of a small, say, hole in the bridge, and the amount of force that is needed to create that hole tells the engineer if that bridge is still strong enough to withstand a certain load. Okay, so you put a little bit of force, a little bit of stress on that bridge, and you see how much of an elongation how much of a hole it creates, or how much, say, extension you get from that stress if it's not a bridge, but let's say some other setup. And we compare it to table values that we expect that material to be like within a certain limits. And if material is strong enough, you are within the limits, no construction is needed, no repairs are needed. But if you have less than expected, then you clearly want to reinforce that bridge and probably just build a new one. So a very important procedure to figure out if a certain system can withstand a certain load, and if you have to replace that system altogether with a new one. It should always stay within the elastic region. That's the general rule, and that's it. Light force, but also on its length. Yeah, it's not just a one-dimensional story. It can be cross-sectional areas, so 2 dimensions, and even for the whole volume, like 3-dimensional stress is also possible. We are not going to do any of that. It's only going to be a single dimension, just the Young's modulus. That's it for this class. So on to the calculations, on to the definitions. From elasticity, we have 2 big components. The first component is what we call the stress. And any stress, one-dimensional, two-dimensional, it's always a force per certain area. Okay, force per certain area, that's what we call the stress. And the strain is the change in a certain parameter. For this class, it's only going to be just length. For 2 dimensions, of course, it's going to be length and the width, but don't worry about 2 dimensions, just 1 dimension. With respect to the original size, for the original, say, length or width or height. And you can connect stress to a strain with what we call the Young's modulus. Young's modulus is just a coefficient that connects a certain stress to a certain stress strain that it produces. If there is a stress, if there is a certain force acting on an object, there would be some kind of an elongation or compression for that object. And you can calculate the amount of force or the elongation or compression based on the other parameters. And Young's modulus is a very well-known number for all the materials. There is a table. Do I have it here? No, I don't have the table here, but the textbook has the table with all the values for Young's modulus, and depending on the material that is given in the problem, you just look up the Young's modulus for that material and plug it in instead of this capital E. Capital E is the Young's modulus. And then you can either calculate the force that is needed or the elongation that the force produces, doesn't matter. So force over area, elongation with respect to the original length or width or height. That's all you have to do. Literally, that's it. End of story. Nothing else from elasticity. The simplest possible scenario right here. Yeah, it's either tensile stress, that means stretching, or compressive stress, that means compression. So those columns in the Coliseum, they are under compressive stress, but if you think about some kind of elongation, then it's tensile stress. So 2 kinds of stress. That's just the way you implement the stress. Do you want to compress something and see the change with compression, or you want to extend something and see the elongation? That's the main difference. Yeah, so depending on the material, it can be either high compressive strength but very low tensile strength, or vice versa. You pick the materials based on those strengths. And our freeways specifically, they are made of concrete because it can withstand a lot of compression. The car goes on top of that surface and there is compression, but concrete is capable of withstanding those large loads from heavy 18-wheelers or semi-trucks or whatever. And it is expected that that concrete will survive for 10 years, 20 years before some cracks will appear. Yeah, shear modulus, it's your two-dimensional setup. Once again, only the Young's modulus is considered for this class. We're not going to do any crazy two-dimensional analysis. Or you have the third one is the bulk modulus. That's the three-dimensional stress that you put on the system. We're not going to do that as well. So yeah, here it is. It's in the textbook, but do not worry about it on the test. Just the Young's modulus. This is your main equation. Stress over strain. Stress is force per area, and strain is elongation or compression with respect to the original length, width, or height. There is this little problem with balancing a wobbly table. I'm pretty sure you've noticed that some tables do wobble, and it's kind of annoying. So in order to solve the problem of a wobbly table, you can put a huge load on top of it, say 290 kilograms on top of the table, and legs would be compressed. You will put some stress, and stress will create some strain. Specifically for this time, it's going to be compression. And if legs are made of wood and they're approximately cylinders, then here's the Young's modulus for the wood that you borrow from the table in the textbook. And the reaction forces on the legs from the floor is the question. Very easy scenario because you have a balance of forces and all legs undergo that compression, but one leg is what? The fourth leg is longer by a little bit, and this is the difference between the compression of other three legs and the fourth leg. So compression of the fourth leg is the compression of the three legs and the difference between the original size of three legs and the fourth leg. Force over area, this is the stress. Elongation versus the original length is the strain, and the Young's modulus is right in the middle. Let's take a look. If you want to solve for stress, it's Young's modulus times the strain. So stress is strain times the Young's modulus. That's what I have here. Stress is Young's modulus times the strain. And from here, you solve for the strain, you solve for the elongation, replace the values for elongation as a expression coming from this Young's modulus definition, and you end up with this equation. So balance of forces plus the Young's modulus, boom, you can solve the wobbly table problem right away. Yeah, you have three forces from three legs and the fourth force from the fourth leg, and it's the gravity from the load that is the force in the opposite direction. Balance of forces means you have zero on the right side. And the previous equation, I'm just copying it here. So this is the system of equations. F sub 3 and F sub 4 are the unknowns, two equations, two unknowns, easily solved with substitution method or elimination method, doesn't matter. The point is, without the elasticity, without the stress and the strain, you can't really solve it. You have this equation from balance of forces, but you only have one equation with two unknowns. You do need the second equation from elasticity in this case to be able to solve it. Many other things are solved with this elasticity approach. That's why we spend time on elasticity in the first place. Once again, for your tests, for your quizzes, all you have to do is just keep in mind this connection between the stress and the strain. I'm going to give you a force. You should be able to solve for the elongation. Or I'll give you the original length of elongation. Tell me what kind of area are we talking about. Something like that. Yeah, this is the worst case scenario, the fracture. If you put too much stress, then you will break the setup. For the general rule on how much of a stress you can put on a system, it should be no more than 1/3 of the ultimate strength of the material. So whatever is the Young's modulus, you shouldn't load it more than 30% of what is expected. If you load more than 30%, chances are you're going to get into this fracture zone. There is a problem on will the bones break if you put a certain stress on your arm or leg or whatever, I don't remember. And you just have to compare the stress that is given to the ultimate stress, the ultimate strength of a bone. The bone is also a material, so you can find the Young's modulus for bones in that table as well. So just look up the Young's modulus. Even though it's not, even if it's not given to you specifically, you can still look it up in the textbook and consider that being given. On the test, of course, you don't have to look into any tables. I will give you all the necessary data for solving for either the strength or the stress. So don't worry about it. Just do the homework and you will you'll be in a good shape. Yeah, you can do a lot of crazy stuff with stones and bricks. The semicircular arc is one of the examples when you actually put a stress and you make the whole construction sturdier. It's going to withstand larger loads. That's why you would see all of those domes, cathedrals built in that way, and they're still standing. See how stones or bricks in a round arc are under compression because the top layer would put a pressure on the bottom layer, and that is your key to strengthening the structure. So the whole structure is going to be it will be able to withstand larger loads. That's the idea behind. For example, we got a pointed arc that require considerably less horizontal force. Here is the force that is given, and here is the reaction, and here's the side force that we want to withstand. So let's say the axis of rotation is where? Is it this one? Is it this? This is the point. Let's see. -2 times 6 times 10 to the 4th. Okay, 6 times 10 to the 4th, that's the force. And it's negative because it creates what? Clockwise rotation. So with respect to this point, yeah, 2 is the moment arm. If this is the line of action, this is the shortest distance. This is your moment arm. And it's negative because it's clockwise. Then you have 4 times 6. Where is the 4? Let's see. Yeah, the 4 is your vertical F sub V reaction. So this is the line of action. That's the axis of rotation. The shortest distance between the axis of rotation and the line of action is 2 and another 2 because the total is 8. So the half of it is 4, and now it's positive because this force creates counterclockwise rotation. So this one is negative, this one is positive. And then the horizontal force that is unknown, we want to withstand that force so that the whole cathedral stays stable. Say this is your wind that blows in that certain direction, and you want the arc to withstand that wind. So that's the line of action. That's the axis of rotation. That's the shortest distance, so 4. So the unknown force times the 4 being the moment arm, and what kind of rotation from this force? It's clockwise. So clockwise means it's negative. So negative 4 is the moment arm, force is given, this is the torque. So this is the balance of torques for this dome of a cathedral if you have a certain load from the materials that it's made of versus the reaction from the bottom part of the cathedral, and say the wind that blows from the side. See how it really doesn't matter the setup as long as you have forces and you want to know how much of a load you want to withstand. All you need is just balance of torques plus balance of forces, of course. If you don't know enough of the forces themselves, you can solve pretty much everything. And if balance of forces and torques is not enough, then you look at elasticity and you can still solve it for those what we call indeterminate cases. Turns out you can withstand what 30 kilonewtons of that side wind, which is a good result because well, it's hard for that wind to create such an enormous load on your cathedral. Okay, this time your cathedral is 8 meters in height. It was 4, now it's 8. You do the same thing, same calculations, and you end up with less of a force that you can withstand from the wind. Well, that makes sense. That just the result of the analysis of a balance of torques equations and just another application of statics that you can see here. So the higher the cathedral, the less side load it can withstand. That would be the result of this discussion. Yeah, so a dome or an arc, doesn't matter, 2-dimensional, 3-dimensional problems. For 2 and 3-dimensional problems, you just have to go with shear modulus or bulk modulus, which we're not going to discuss in this class. But once you take statics course, you'll be familiar with all of those tables and values, and you'll find the best materials that are capable of withstanding the most loads. That's what the statics is all about. Okay, that's the end of lecture. Let me stop the recording and we'll do the classroom discussion.